Okay, investigation 2.2, instantaneous rates of change. It's supposed to be rates. Okay, and we're going to talk about this application. So, in 1997, Donovan Bailey ran a 100-meter sprint in 9.77 seconds. The table below describes his run. One model describes this run as a quadratic model with the equation. Here we go. Okay, so we remember this from the prior investigation, but this time what they did is they modeled the run with this quadratic. Okay, so we still have this table of values, but now we have an actual graph that's fluid and consistent. Okay, so let's talk about this. Estimate Donovan Bailey's instantaneous velocity at 6 seconds. So I'm going to kind of blend number 1 and number 3. Plot a point on the curve at 6 seconds. So if we take a look at 6 seconds, and I'm sorry, this cut off, this is time in seconds. If we take a look at 6 seconds, we follow all the way up, we are about here, okay? In other words, we are approximately at 55 meters. So in 6 seconds, he has run 55 meters. That is real quick. So in C, I'm going to do C first. Draw a line that passes through this point, but does not pass through the curve again. This is called a tangent line. That's the entire purpose of doing an instantaneous rate of change. And next semester, this will be the basis of calculus, okay? So we are going to make sure that, see how like this kind of curves up like this? This is a very, very extreme, but it curves, this line, or this curve curves up. So I'm going to make this tangent on this side. Boom. It hits at one point, and then it keeps going up, okay? And it never hits again. So a line that crosses a curve at a single point is called a tangent. At 2 points is called a secant. That would be for average rate of change. That's the difference here, okay? So tangent, let's estimate, let's go, it's almost like this. And by the way, I'm plotting this on the tangent. So on the tangent, I'm not plotting this on the curve. So that would go from 55 to 45, so that would be 10. And that would go from 5 to 6, that would be 1. So estimate Donovan Bailey's instantaneous rate of change at t equals 6 seconds. So m equals 55 minus 45 over 10 minus 1. And we get, or sorry, why did I put 10 minus 1? I was thinking 10. 6 minus 5. Those are the points that we're using. And we get 10 over 1. So 10 meters per second. Okay? And now explain why you think your answer in part A is a good approximation. So it's definitely approximate, but what we did is we graphed the line, okay? So I think that it's a good approximation because we graphed the line. So we graphed the tangent, let's call it, be specific. We graphed the tangent, and we see the point, let's go 5, 45, approximately lies on the tangent. Okay, and we see the point 655 is our original point. Like, so that one's given. So I'm just gonna put is given, right? And then we use the slope formula. And we used the slope formula. Okay, so that's why I think it's a good approximation. Okay, number 4, use the algebraic model d at t equals 0.28 t squared plus 8.02 t minus 2.54 to approximate the instantaneous velocity at Donovan Bailey at t equals 6 seconds. Okay, so now let's actually solve for this by completing the charts below. Okay, so what we're going to do is we're going to use average velocities to approximate. So this is what we're going to be doing. Delta D would be the change in D. So we see the intervals here. So we see each interval starts at 6. Okay, and then this is the interval from 6 to 7. So that's like a difference of 1. And then we're going to get smaller. We're going to get, okay, well, let's bring this point closer to 6. What about 6.1? That's pretty close. All right, now let's bring that point even closer to 6, 6.01. Okay, now let's bring that point closer to 6, 6.001. Okay, so now we start with like being 1 point away from 6, and then now we're decimal 001 points away from 6. So take your calculator, and I'm going to do these quickly, but you can fill this out. Find D at 7. Well, D at 7 is 67.32, and then D at 6 is 55.66. So what I get for the answer here is I get 11.66. Okay, the difference here is 1. So now when we do the average velocity, we go 11.66 divided by 1. So this is 11.66, and this is already saying meters per second, so I'm not going to rewrite it, okay? Now let's do the next one. So 6.1, when we plug in, so this is essentially D at 6.1 minus D at 6. Okay, so I get 56.8008 minus the 55.66. This one's not going to change. Okay, if you plug in D at 6, you're going to get 55.66, obviously every single time. So we're going to use that all the way down. So not too many calculations there. And I get 1.1408. So the difference between 6.1 and 6 is 0.1. So 1.1408. Oh, is there an O in there? Yeah. Divided by 0.1, I get 11.408. So if we're taking a look here, these numbers are actually quite similar. Okay, now let's do the next one. And so I'm going to write this out one more time, and then I'm not going to write it anymore. So D at 6.01 minus D at 6. So what we're going to get for that one is 55.7738 minus 55.66. 0.1138. Okay, 0.01, or sorry, 6.01 minus 6. That's a difference of 0.01. Okay, so I'm getting 11.38. Okay, 6.001. I'm going to get the numbers 55.67138. We're going to subtract 55.66. And we get 0.01138. Okay, so if we were to divide these, we get 0.01138 divided by the difference, which is 0.001, and we get 11.38 again. Okay, probably more decimals here, which is absolutely fine. However, we're going to just like round to those 2 decimals. I mean, this one we rounded to 3, that's totally fine too. Okay, but we can see a trend now. So let's talk about this. As we get closer and closer from 7, so this is the 0.6, and then this is the 0.7. As we get closer and closer to 6, so this is like 6.1, this can be like 6.01, right? As we get closer and closer to 6, that tangent line, or you know, what we're essentially making here when we do the average velocity is we're making a secant line. So a secant goes between these 2 points, or these 2, or these 2, or these 2. Okay, we're making a secant line, but it's getting so close to 6 that it's almost 6. All right, now let's talk about the interval on the other side of 6, right? So we talked about how like 6 was here, 7 was here. Okay, but what if we went down to 5? What if we came in, so we talked about 7 going into the 6. What about if we talked about the 5 going into the 6 from the other side? So we would have like 5.9, 5.99, and then right in there 5.999. Okay, let's talk about that. And again, I'm going to skip the function notation here, and I'm just going to write out the numbers. So D6 minus, D6 minus D5, I get 55.66 minus 44.56, and I get 11.10. Okay, but the difference in 6 and 5 is 1, so 11.10 divided by 1, again, 11.10. Now, what if we get closer to 6? So we're going to have that 55.66 again, but this time we're going to subtract 54.5248, 1.1352. Okay, 6 minus 5.9, I get 0.1. So divide these out, and I get 11.352. Okay, next one, 55.66 minus 55.5462. Okay, we can see that the numbers are getting very, very similar. Okay, so this is a difference of 0.01. So we get 0.1138 divided by 0.01. And I get 11.38 again. Wow, super similar. We saw that up here. Okay. And 55.66 minus 55.64862, 0.01138. Okay, so if we took 0.01138, we divided out 0.001. Again, the difference between the x's, we are going to get 11.38 again. Okay, so lots of just calculations here. So let's actually talk about what's going on here. So as we come closer and closer to 6, as we go in and in, right, we're essentially, again, average velocity, we're using the slope, we're essentially drawing like a secant between 5 and 6, and then 5.9 and 6, then 5.99 and 6, and then 5.999 and 6. Okay, we're drawing these secants that are getting infinitely close. Like, if we look at this one, there's only a decimal 0.001 difference between these two numbers. So that secant line is going to be so small that we can almost consider it a tangent line. Okay, so what did this actually ask us to do? Use the calculations from the charts to approximate the instantaneous velocity at t equals 6. So here's the thing. Here's 6. When we take a look at the 5 going into the 6 and the 7 going into the 6, what do we notice? Well, in this chart, what do we tend to? We tend to 11.38. In this chart, what do we tend to? We also tend to 11.38. So I'm going to estimate that our instantaneous rate of change, IROC, equals 11.38 meters per second. Okay, ensure that you use the meters per second here. Okay, and we kind of already talked about number 6. If you could draw secants that correspond with these average velocities, how could they compare to the tangent? Right, we talked about that. As these secants get, like the difference in the x's get smaller and smaller and smaller, it almost tends toward a tangent.